Welcome to this Sigma Aldrich seminar series. Today's topic is on choosing fluorophore quencher combinations. My name is Anders Bergqvist. I will talk a little bit about the fundamentals of fluorescent energy transfer and how it's influenced by the molecular structures of the fluorophore dyes and quenchers. I will talk some about practical considerations for choosing fluorophores and quenchers and include tables of common fluorophores and quenchers suitable for qPCR assays. It is illustrative to consider the spectral range of electromagnetic radiation. Within this range, what we human beings consider to be visible light is just a narrow band ranging of wavelengths approximately from 400 to 700 nanometers. At shorter wavelengths, we have more energetic radiation types, such as ultraviolet, X-ray, and nuclear radiation. At longer wavelengths, we have radiation types that are more suitable for transmission over longer distances, such as infrared, microwave, and radio frequency radiations. The first law of thermodynamics states that energy is conserved. An isolated energy quantum may thus be transferred, by splitting to lower energy components, to longer wavelengths radiation types, but not vice versa. In other words, isolated radiation can be transferred from blue wavelengths to red wavelengths, but not vice versa. This may thus be useful to remember as we continue this presentation. In general, a fluorescent molecular entity will accept the radiation at a particular wavelength, possibly at a blue wavelength, and it then enters an excited state. While in an excited state, losses may occur by heat transfer or other vibrational or rotational motions. These losses generally occur at wavelengths near infrared wavelengths. The remaining energy is finally released at a characteristic emission wavelength more towards the red part of the spectrum compared to the original excitation wavelength. An observer may set up a detection system at the emission wavelength to specifically detect presence of fluorescence event. In qPCR and in other applications, we often use molecular quencher entities to absorb emission radiation of observed fluorescent entities. As before, the fluorescent entity accepts radiation at a particular wavelength and enters an excited state. Losses occur at longer wavelengths, and the remaining energy is released at the characteristic emission wavelength. However, this time the emission from the fluorophore dye is absorbed by the quencher, since the emission wavelength of the fluorophore dye matches the excitation wavelength of the quencher. The quencher then in turn gets excited, loses energy at longer wavelength, and potentially also releases remaining energy at another characteristic wavelength. However, the characteristic emission wavelength of the quencher is selected to be sufficiently different than the characteristic emission wavelength of the fluorophore dye, so that detection aimed at the fluorophore dye emission wavelength will only detect signal from the fluorophore dye. Some efficient quenchers have no particular emission wavelength, but dissipate all energy through heat transfer or similar processes. Another way of illustrating the energy transfer action of fluorophores and quencher is with a Jablonski diagram. The excitation radiation corresponds to a certain large energy excitation from the base level of the electronic orbital that is responsible for the fluorophore action. Over some short time, energy is lost through small steps between quantum energy levels, and finally there is a larger release of emission radiation, corresponding to the final step toward the base energy level. With a quencher in place, the remaining energy is instead transferred to an electronic orbital of the quencher. Energy losses occur through small steps between quantum energy levels, and finally there is a potentially large release of the quencher emission radiation. But this emission energy will be different from the emission energy of the fluorophore dye. It was understood from the Jablonski diagram that electronic orbitals determine excitation and emission characteristics of fluorophores and quenchers. Electronic orbitals come in many different shapes, and the benzene molecule is useful to illustrate some of them. The electronic orbitals include sp and p orbitals. Of particular interest to us is the delocalized pi orbital that contribute to conjugated systems that allow particularly useful excitation and emission properties. One example of a conjugated system is present in the retinol molecule of vitamin A. Retinol is an important cofactor in protein molecules that provide ability to perceive light to, among others, humans. Retinol could thus be said to be a good representative example of the kind of molecule that responds to radiation wavelengths in the range of visual light. Fluorophore dyes and quencher molecules often share features of conjugated systems. Fluorescein is a fluorescent moiety that forms the basis for one of the most popular family of fluorophores. This family includes FAM, Hex, Joe, Tet, Rox, Tamra, and Texas Red, all of which are slight modification of the underlying fluorescein molecule. The complexities of the molecule and the details of the modifications contribute to several overlapping excitation and emission energy transitions. This leads to complex excitation and emission spectra. This spectral diagram illustrates the complex excitation and emission spectra of fluorescein. Note that the complexity is even more involved, as each of the excitation and emission spectra depends on their respective emission and excitation radiation wavelengths. Another family of fluorophores is the cyanin family. Cyanin dyes are molecules where two nitrogens are joined by a polymethane chain. Cybergreen is popular due to its ability to intercalate double-stranded DNA. Cy3 and Cy5 are popular fluorophores in the middle to long wavelength range, and they also have favorable quenching properties for many other fluorophore dyes. Quenchers have the desired feature to have a lot of rotational and vibrational degrees of freedom in order to dissipate as much of the absorbed radiation as possible while minimizing the amplitude at their own characteristic emission wavelengths. Classical examples of quenching molecules include Dabsil and Tamra. A variant of Dabsil is shown here. Black hole quenchers are very efficient and have virtually no significant emission signal. BHQ1 is shown here. It is worth noting that nucleotides themselves can act as quenchers in fluorescent assays. In particular, guanine is an efficient quencher, and it may be desirable to avoid guanine in positions adjacent to your fluorescent dye moiety. In this illustration, the X denote nucleotides in the probe sequence, and the N's denote complementary nucleotides in the template sequence. Depending on your assay, presence of guanine in the probe or template sequences adjacent to the fluorophore may decrease assay efficiency. In general, many parameters need to be considered for a proper selection of fluorophore dye and/or quencher molecule. These include the ability of the molecule to absorb light. This is the extinction coefficient. The quantum yield of desired radiation-induced processes. This is the ratio of the desired event to the number of photons absorbed by the system. The Stokes shift is the difference between the excitation and emission maxima of the fluorescent molecule. A large shift is often desirable to avoid leaking of excitation radiation into the emission detector. Photobleaching is the photochemical degradation of the fluorophore. However, stability to photobleaching is not as important for qPCR applications as it may be for other applications. Stability to varying pH conditions. However, fortunately for us as qPCR users, fluorophore dyes and quencher molecules have been developed that are very well suited for qPCR applications, and it is often a matter of simply selecting appropriate dyes and quenchers from a prepared table of pre-selected entities. This is a table taken from the Sigma-Aldrich website with fluorophore dyes suitable for qPCR hydrolysis probe assays, covering a range of excitation and emission wavelengths. BHQ quenchers have outstanding properties for this application, and as can be seen, the excitation maxima of BHQ1, BHQ2, and BHQ3 match close to emission maxima of compatible fluorophore dyes. Another consideration that needs to be made is the compatibility with the instrument that is going to be used. The following is a list of the more common instrument and fluorophore combinations that is available from the Sigma-Aldrich website. Red dots in the table indicate compatible combinations. More detailed information can be obtained from the instrument manufacturer. In this presentation, we first consider some fundamental biophysical concepts such as molecular energy transfer and electronic orbitals, and how they relate to observations of light wavelengths and spectra. We mentioned how small molecular modifications can lead to important changes to spectral and/or biochemical and/or biophysical properties within families of common fluorophore dyes and quencher molecules. Although modern instruments handle large ranges of fluorophore dyes, some care needs to be taken to assure compatibility. The Sigma website is a useful resource with the lists of standard qPCR and other molecules. Consult Sigma experimental design and data analysis at www.sigma.com/designmyprobe for additional support and answers to direct questions. We enjoy being a small part of your scientific project, and we offer free personal advice on many qPCR topics. We have online tools available directly at our site, and we can also perform personalized services for you. We are happy to assist you regardless of what products you are using at the moment. While planning future experiments, have you considered Sigma's range of qPCR reagents and kits? Use a combination of Sigma services and products for guaranteed success. This was a brief overview of considerations for choosing fluorophore quencher combinations. I hope you enjoyed it. Look out for more presentations in the Sigma Older series. Thank you for your attention.